Right now, last week we mentioned about the momentum equation. Also, we talking about some simplified momentum equation, especially go to the Euler equation or binary equation. From the momentum equation, if we don't consider the viscosity, we can consider this as the ideal case. So last time we used some vector identity to show if you from the Euler equation, you do the integration, then you can get the binary equation. So far, any question about that? The momentum equation basically are talking about the acceleration of the external force. So this kind of external force, in some case, then we do the work. If this kind of force, they have some kind of working distance. So you have external force times the displacement. They will become to the force, but they will become to the work. But in more general case, you will get the working rate. So the working rate is similar like the work, because if you differential the work with the time, then usually you will time the external force with the velocity. So external force times the velocity, usually that is the working rate, or sometimes they mention as a power. So for example, if you buy a car or you buy a motorcycle, usually they will give you some kind of the power of this car or power of this motorcycle. Basically, they are talking about how much external force they can give from this engine. So depending on your car mass, this external force will decide your acceleration of a car. Then different velocity, they will have a different kind of external force, and also the velocity correspond to the engine. For example, like the car engine or motorcycle engine, that is not like the force. The engine is like the rotation. So usually they will give you a torque and the rotation speed. So when you drive in a car or you have a motorcycle, you will see the RPM. That means your engine, the rotation speed, and usually from this rotation speed, you will find the torque as well. Torque times this rotation is equivalent to the external force times the velocity. Okay, so this is in the some kind of you design some vehicle like a motorcycle, or you design some kind of car, they will consider. Okay. Okay, so because we talk about momentum equation, so here, basically in momentum equation, we are mainly mentioned about the external force. But in some case, for example, like the energy equation, we will use the work. So the external force, if you want to do the work, you must have some kind of displacement, like this. Otherwise, no, they just didn't output the work. Okay. Then the power compared to the work, basically usually differential with time, or you just take the time average. Then you will get the power. So for the constant external force, or maybe your force can change with time, doesn't matter. Then you need to do the integration if your force change with time. Then displacement, you maybe change with time as well. That's change velocity. But for simplify, you just consider constant velocity. That will be the easy case. So that's the power related to the work, their relationship. So we give an example is like if you have a car, your car power, and you have some kind of velocity. Then if you want to keep this velocity, you must have some kind of external force to balance maybe the air pressure from the flow. This kind of external force you must balance, then you keep a constant. Then if you have an additional force, then you will make this car acceleration. So that's why the car higher is more difficult to have a acceleration. So we talk about if we have an engine, the engine output is not like the external force and the velocity. Your engine is the rotation. So your engine rotation basically they have some kind of torque, and they have some kind of rotation velocity. So they come out with one question. This one, if we have a car, we choose certain of engine, or we have airplane, we choose certain of engine. They have a torque and this kind of rotation rate. Compared to real performance of this car or airplane, which one will be larger?
The question?
The-
Can you please repeat the question?
The question?
Yes.
The question is if we choose the engine, then engine give us some kind of spec. That spec is some kind of power. and this power should be some kind of a torque and some kind of a omega. So for example, if we have 100 RPM, then we have a certain of torque. Then our output, for example, is like 1,000 watt, 1 kilowatt output. And put into a real car or put into a real airplane. Similar, we have some kind of output, external force. Then we make this airplane or this car with some kind of velocity. But in reality, this compared to this should be different. Then the simple question is which one is larger? The engine is larger. Why? Yeah, there are some kind of transmission loss. Because this is the original power. Then usually they have some kind of expansion, some kind of gear. Then they should transfer to maybe the tire, maybe sometimes like an airplane, then maybe just like an output. But they must have some kind of loss. So in reality, you need to consider the design loss. But basically, these two are linear proportion. Okay, so that's usually if you want to design some kind of a moving vehicle, no matter ship, car, airplane, it's similar like this. You design some kind of a shape. This shape give you certain of a resistant force and the friction. Then you must resist this kind of friction. For example, if you design some kind of square car, you have a very large friction. If you design some kind of a straight line, okay, then same engine, they will give a different performance. Then your engine choose, of course, higher power give you higher force, but higher power you consume more energy. So if you buy some kind of a big car, like a Mercedes-Benz, then you put a gasoline just like put a water. They drink this gasoline like drinking the water. Okay. Okay. So the last time we also talked about from the Euler equation. If you do the integration, then doing the integration, basically you use the first vector identity. The second, you do the integration along the straight line and with the convection term. So last time we mentioned this convection term will become to 0 after the vector identity. Then because this integration is only convection term for this part. For this part, then we have a local derivation for this. Because the steady flow, local derivation will just become to a 0. Okay. So today we will use this again because I must emphasize this because all the Gaussian equation, mass, momentum. Today we talk about energy. Even for this binary equation, if you want to see the certain of a particle, you must follow this particle. If you want to follow this particle, then you need to do this material derivation. Or sometimes they mention this as a particle derivation because we follow the certain of a particle. But the flow theory is described by the space parameter SYZ and also the temporal variable by the time. So if we take this particle derivation into the field derivation, we need to do this kind of material derivation transfer. Okay? So then we have a local derivation term and the convection derivation term. So last time we talked about this convection derivation term equivalent to 0 for the steady flow, this material derivation. Then we make sure become to 0 because it's steady flow. But for unsteady flow, it's not. Okay? So that's I'd like to mention about that. Then today we're going to talk about energy equation. Or you maybe already see in the first law in thermodynamics. I will more focus on the force, especially in the work part. So in the force, that's come from the momentum equation. So you will see in the momentum equation, external force, we will consider the pressure. The pressure, like I mentioned, basically in binary equation, they are conserved. They can transfer to a different kind of energy. So that energy should be like the particle in this. Later on, I will talk kinematic energy, potential energy. They will transfer. But viscosity force, usually we will mention as friction force in the flow. So we will see this kind of friction force, how to, it's not contribution, it's dissipate, because they always reduce useful energy. So if contribution, yeah, there's negative contribution, okay? They will reduce useful energy. So both come from the force, but they will contribution to the work. And the energy equation, the statement is like this: work and the heat. And I like to emphasize again the system. Okay, the system sometimes mentioned as a particle. This system, or sometimes they mention as a parcel. The parcel is a many particles get together. That's parcel. But anyway, they are look original part. Okay, just like you got system, because you registered in this semester. So look like today some particle not coming. Some students are coming. So the system is not complete. Okay, but you can see this control button are the same. Okay, so that system and the control button, their difference. This is the definition for the energy equation, and the first, the textbook write down like this: the dT, total of energy change, is equivalent to the external heat add in or heat go out of this system, and the work similar. So here they use a dT, but in some textbook they will use a delta. So what difference between these two? Have you guys looked this symbol? But in this university, they use the textbook, it's like this. If you take the thermodynamics in this university, you should know what difference between this D and this delta. One is English, one is Greek. But in physical, what difference? This X undergraduate student take in this university. Can we know?
delta 尺度会比较大。
尺度会比较高。
比还要再大一些。
那你的学长？
焦糖是路径很疏的意思。焦糖是因为那个是路径很疏的意思。
Okay, exactly. So you not take a you take an undergraduate from another university. Okay, your instructor talk about this. Supposedly they will talk about difference. One is the pace function. One is the state function. Okay, so I should write down this because you talk. This is a state function. Okay, so have you guys talked about this? Did you talk about pace function and state function? Do you go to a class? No, you didn't go to a class. Of course, you don't know. How about Chen-Bo? No, you go to a class. That's the important thing because you cannot stay at home, then X instructor give you some kind of information to your home. They must give the information in the lecture. And usually, this function is mentioned as a state function. That means you determine this internal energy change depending on their final state and the initial state. Doesn't depend on the path. So for example, you have a same state 1 to another state 2. You have a different path. Different path in this example is a different kind of work. Okay? So but some people use this but more accurate, more precisely representations use delta because they will change with a different pace, no matter the heat and the work. And when I teach thermodynamics, usually I will tell the student similar to the graduate student. Okay, if we take the exam, usually we just look your state. We give an exam question. We just see if you can answer or not. So we see your state. Then, which kind of path you want to go? Some people use a long path, but take a lot of energy. Some people maybe can go very short path, take less energy. So that means your working efficiency is very good. So that's your approach, okay? But usually we just see it in the exam or in the different kind of qualify, or you want to get some position. Usually people just look your different kind of step. Okay. So every student come in this university similar. They have a different kind of step. But the purpose for this university or the purpose of maybe this class, we try to increase your step as much as possible. So we take some kind of a path, but that's instructor path. If you don't take your effort, you didn't take your path, then I don't think this will increase. Okay? So that's some kind of a thermodynamic to maybe your personal status. Okay. Then for the internal energy, just like we mentioned, the total energy we will consider the internal energy and the kinematic energy, and also the this is the potential energy. So how can we determine the internal energy? Or maybe this symbol you are not quite familiar. In the thermodynamic, this is like a internal energy. They show a person name, but different symbol. Okay, so for total energy, we will consider one internal energy, and the other is the kinematic energy and the potential energy. Just like we mentioned, kinematic energy and the potential energy later on they will conserve in the energy equation with the pressure force, so they will transfer. So in certain of special case, pressure, kinematic energy, potential energy, they will just special case. Later on we will mention. For the internal energy, how can you look for the internal energy? And this is a per unit mass. For this is a per unit volume. Okay. Because we kind of low. So if you want to get a total energy, you should find the total volume. Okay. Then so one of the question is how shall we look the internal energy and what's function for the internal energy? Is review thermodynamics. For the graduate school, usually we will review undergraduate because you talk about energy equation. You talk more complete energy equation in the thermodynamics. I think that is the closest everyone took. Then for this thermodynamics, you have a table, and this should relate to the temperature and the pressure, especially the temperature, because in many cases you will just have a constant pressure case. So the So for this internal energy, I like to mention is I try to remind you thermodynamics table. It's not only the U, there is the H, there is the specific volume. Okay, specific volume is the invert of density, and also they have entropy. Of course, we not use S because that will be second law, but in the first law, U will relate to the H. So you should be able to have this ability and the knowledge about the internal energy, density, okay, specific volume, and the density. That's first part of thermodynamics. So we take a break. Later on, we talk about this.